This video provides concise short notes on the main topics of Class 12 Physics, covering essential concepts like electric charges, electromagnetic waves, and alternating current. Each section is designed to enhance understanding with clear explanations and practical examples. By focusing on key principles, students can grasp complex ideas efficiently and prepare effectively for exams. Key concepts related to electric charges and fields include charge conservation, which states that the total charge in an isolated system remains constant. Coulomb's law describes the force between two charges as directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. The electric field is a region around a charged object where a force is exerted on other charges, with field lines indicating the direction and strength of the field. The principle of electric charge conservation asserts that the total electric charge in an isolated system is unchanged over time. This means that charges can be transferred from one object to another, but the net charge remains the same. An example is when rubbing a balloon on hair, electrons are transferred, but the overall charge of the system is conserved. Coulomb's law describes the electric force between two-point charges as F equals K asterisk, Q1 asterisk Q2, slash R squared, where K is Coulomb's constant, Q1 and Q2 are the charges, and R is the distance between them. This law highlights that the force is attractive if the charges are opposite and repulsive if they are like charges. It is a fundamental principle that helps in calculating forces in electrostatic situations. The concept of an electric field is defined as a region where a charged object experiences a force due to the presence of another charge. Field lines are used to represent the direction and strength of the field, with lines pointing away from positive charges and toward negative charges. The density of these lines indicates the field's strength, with closer lines representing a stronger field. The electric field due to a point charge is calculated using the formula E equals K asterisk Q slash R squared, where E is the electric field, K is Coulomb's constant, Q is the charge, and R is the distance from the charge. This field is radial and points away from positive charges and toward negative charges. The strength of the field decreases with the square of the distance, making it stronger when closer to the charge. Electrostatic potential is the work done in bringing a unit positive charge from infinity to a point in an electric field, measured in volts. Capacitance is the ability of a system to store charge per unit voltage, expressed in farads. Together, they describe how energy is stored and transferred in electric fields, with capacitors being a practical application. The relationship between electrostatic potential and potential energy is given by U equals QV, where U is the potential energy, Q is the charge, and V is the potential. This equation shows that potential energy is directly proportional to both the charge and the potential. It explains how energy changes when a charge moves within an electric field, affecting work done and energy conservation. Dielectric materials increase the capacitance of a capacitor by reducing the electric field within it, which is quantified by the dielectric constant, K. When a dielectric is inserted between the plates of a capacitor, it polarizes, creating an opposing field that reduces the overall field strength. This allows the capacitor to store more charge at the same voltage, enhancing its energy storage capacity. A parallel plate capacitor consists of two conductive plates separated by a dielectric material, with capacitance given by C equals epsilon asterisk A slash D, where epsilon is the permittivity of free space, A is the area of the plates, and D is the separation distance. The capacitance is directly proportional to the plate area and inversely proportional to the distance between them. This setup is widely used in electronic circuits for energy storage and filtering applications. The energy stored in a capacitor can be calculated using the formula U is equal to 1 divided by 2 times C times V squared, where U is the energy, C is the capacitance, and V is the voltage across the capacitor. Another method involves using U equals 1/2 asterisk Q asterisk V, where Q is the charge stored. These formulas highlight how energy storage depends on both the capacitance and the voltage applied, making capacitors essential in energy management in circuits. Current electricity involves the flow of electric charge through a conductor, driven by a potential difference. Fundamental concepts include Ohm's law, which relates current, voltage, and resistance, and Kirchhoff's junction rule, which states that the total current entering a junction equals the total current leaving. Understanding these principles is crucial for analyzing circuit behavior and ensuring efficient energy use. Electron drift is the slow movement of electrons in a conductor when an electric field is applied, with a typical drift velocity of about 1 millimeter per second. This drift is influenced by factors like temperature, material properties, and electric field strength, which also contribute to resistance. Resistance arises from collisions between electrons and atoms, impeding the flow of current and converting electrical energy into heat. Ohm's law defines the relationship between current, I, voltage, V, and resistance, R, with the formula V equals I asterisk R. This law implies that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points and inversely proportional to the resistance. It is a fundamental principle used to design and analyze electrical circuits, ensuring safe and efficient operation. Electrical power in DC circuits is calculated using the formula P equals V asterisk I, where P is the power, V is the voltage, and I is the current. This equation shows that power is the rate of energy transfer and is measured in watts. Understanding this concept is essential for determining the energy consumption of devices and optimizing circuit efficiency. Kirchhoff's junction rule states that the sum of currents entering a junction equals the sum of currents leaving it, ensuring charge conservation in circuits. This principle is crucial for analyzing complex circuits, allowing engineers to determine unknown currents by setting up equations based on this rule. For example, in a circuit with 3 branches, if 2 currents entering are 3A and 2A, the outgoing current must be 5A. The key principles of moving charges and magnetism involve the interaction between electric currents and magnetic fields, where a current-carrying conductor generates a magnetic field around it. This relationship is quantified by the Biot-Savart law and Ampere's law, which describe how magnetic fields are produced by moving charges. An example is the magnetic field around a straight wire, which forms concentric circles with a strength proportional to the current and inversely proportional to the distance from the wire. Oersted's experiment demonstrated the connection between electricity and magnetism by showing that a current-carrying wire affects a nearby compass needle. When Hans Christian Oersted passed an electric current through a wire, the compass needle deflected, indicating the presence of a magnetic field. This experiment laid the foundation for the field of electromagnetism, illustrating that electric currents can produce magnetic effects. The Lorentz force is the force experienced by a charged particle moving through a magnetic field, calculated using F equals Q, V times B, where Q is the charge, V is the velocity, and B is the magnetic field. This force is perpendicular to both the velocity of the particle and the magnetic field, causing the particle to move in a circular or helical path. It plays a crucial role in devices like cyclotrons and mass spectrometers, where it helps in deflecting charged particles. The magnetic field due to a current-carrying conductor is calculated using the Biot-Savart law, which states that the magnetic field at a point is proportional to the current and inversely proportional to the square of the distance from the conductor. For a long straight wire, the field is given by B equals mu I / 2 pi r, where mu is the permeability of free space, I is the current, and r is the distance from the wire. This formula helps in understanding the distribution of magnetic fields around conductors, essential for designing electromagnetic devices. When charged particles move through both electric and magnetic fields, their paths are altered due to the Lorentz force. This force is calculated as F equals Q, E plus V times B, where Q is the charge, E is the electric field, V is the velocity, and B is the magnetic field. The result is a spiral trajectory if the fields are perpendicular, with the particle experiencing a circular motion due to the magnetic field and a linear acceleration from the electric field. Electromagnetic induction is the process of generating electric current in a conductor by changing the magnetic field around it. This principle is used in devices like transformers and electric generators, where the motion of a magnet relative to a coil induces a current. The phenomenon is governed by Faraday's law, which states that the induced electromotive force, EMF, is proportional to the rate of change of magnetic flux. Magnetic flux is defined as the product of the magnetic field and the area it penetrates, measured in Weber's WB. It plays a crucial role in electromagnetic induction, as changes in magnetic flux through a circuit induce an EMF according to Faraday's law. For example, rotating a coil in a magnetic field alters the flux, generating an alternating current in the coil. Faraday's law of induction states that the induced EMF in a closed loop is equal to the negative rate of change of magnetic flux through the loop. This principle is applied in electric generators, where mechanical energy is converted into electrical energy by rotating a coil within a magnetic field. The law is also used in induction cooktops, where changing magnetic fields induce currents in the cookware, generating heat. Lenz's law asserts that the direction of an induced current is such that it opposes the change in magnetic flux that produced it. This is a manifestation of the conservation of energy, ensuring that the induced current creates a magnetic field that counteracts the original change. For instance, when a magnet is pushed into a coil, the induced current generates a field that repels the magnet, demonstrating the oppositional nature of the induced current. An AC generator converts mechanical energy into electrical energy using the principle of electromagnetic induction. It consists of a rotating coil within a magnetic field, where the rotation induces an alternating current due to the changing magnetic flux. The output voltage varies sinusoidally, with the frequency determined by the speed of rotation and the number of coil turns. In circuits, alternating current, AC, exhibits a sinusoidal waveform, constantly changing direction and magnitude. When applied to resistors, the current and voltage are in phase, while in capacitors and inductors, they are out of phase due to reactance. The behavior of AC in LCR circuits is characterized by resonance, where the impedance is minimized and the current reaches its maximum value. When alternating voltage is applied to a resistor, the current is in phase with the voltage, resulting in pure resistive behavior. In a capacitor, the current leads the voltage by 90 degrees, while in an inductor it lags by 90 degrees, due to the energy storage in electric and magnetic fields, respectively. These phase differences are crucial for understanding power distribution and reactive power in AC circuits. The RMS, root mean square, values of current and voltage in AC circuits provide a measure of the effective power delivered, equivalent to the DC values that would produce the same heating effect. For a sinusoidal waveform, the RMS value is 0.707 times the peak value, offering a practical way to calculate power consumption. This concept is essential for designing efficient electrical systems and ensuring safe operation of appliances. Phasor diagrams are graphical representations that illustrate the magnitude and phase relationships of alternating currents and voltages. By using rotating vectors, Phasors simplify the analysis of AC circuits, showing how current and voltage are related in terms of phase angles. These diagrams are particularly useful in complex circuits involving resistors, capacitors, and inductors, aiding in the visualization of impedance and reactance. In LCR circuits, power is calculated using the formula P equals 6 cos phi, where V is the voltage, I is the current, and phi is the phase angle between them. Resonance occurs when the inductive reactance equals the capacitive reactance, minimizing the impedance and maximizing the current. At resonance, the circuit behaves as a pure resistor, and the power factor becomes unity, leading to maximum power transfer. Electromagnetic waves are transverse waves consisting of oscillating electric and magnetic fields that propagate through space at the speed of light, c equals 3 × 10 to the power of 8 m/s. They form the electromagnetic spectrum, which includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, each with unique wavelengths and frequencies. These waves are crucial for communication, medical imaging, and energy transfer, showcasing their versatile applications in technology. The concept of displacement current was introduced by James Clerk Maxwell to account for the changing electric field in capacitors, completing the Ampere-Maxwell law. It is defined as I_d equals epsilon d phi_e/dt, where epsilon is the permittivity of free space and d phi_e/dt is the rate of change of electric flux. This idea is essential for understanding how electromagnetic waves can propagate through a vacuum, as it allows for a continuous flow of current in the absence of a physical conductor. The electromagnetic spectrum encompasses all types of electromagnetic radiation, categorized by wavelength and frequency. Key components include radio waves for broadcasting, microwaves for cooking, infrared for heat sensing, visible light for sight, ultraviolet for sterilization, X-rays for medical imaging, and gamma rays for cancer treatment. Each type of radiation has distinct properties and uses, making the spectrum a fundamental tool in science and technology. Wave propagation of electromagnetic waves involves their transmission through different media, such as vacuum, air, and glass, with varying speeds and behaviors. In a vacuum, they travel at the speed of light, while in other media, their speed is reduced due to interaction with atoms. This interaction can lead to reflection, refraction, diffraction, and absorption, affecting how waves are used in communication, optics, and remote sensing. Understanding electromagnetic waves has led to practical applications like radio broadcasting, where waves are used to transmit audio signals over long distances. Microwave ovens utilize these waves to heat food by causing water molecules to vibrate, generating heat through friction. In medical imaging, X-rays, a form of electromagnetic radiation, penetrate the body to create detailed images of bones and tissues, aiding in diagnosis and treatment.